This is going to be the highlight of our program. Our keynote speaker.
My name is iPal, and I want to finally tell you about my cousin Rover.
Oh my gosh, this Rover thing again. Your cousin. Okay, tell me about Rover.
Well, thank you for finally asking. 8 years ago, he went on a trip to Mars. I miss him very much. I have been trying to call him on Mars, but no one can help me. Mr. Bowani told me they have invited a dear guest today, and I want to see if he can help me talk to Cousin Rover on Mars.
We were going to help you with that. We do have a very special guest, and our special guest is going to help you get in touch with your cousin Rover. So if you could just stand there nicely and politely, we'll get our speeches going, and we're going to help you get connected. Ladies and gentlemen, I'm thrilled to introduce our next guest, but really he does not need an introduction. Dr. Firouz Naderi has dedicated his career to something we've been talking about here today. You have to have the passion, you have to have the desire, you have to have the drive. And he's done all of that when it comes to space, science, and exploration. Dr. Naderi is the former director of solar system exploration at NASA's JPL, where he spent more than 30 years in various technical and senior executive positions. Best known for his leadership of the Mars exploration program, he has contributed to some of the most iconic NASA robotic missions to various corners of the solar system. He's been honored multiple times, including NASA's highest award, the Distinguished Service Medal. In March of 2016, as you might have already heard, an asteroid was renamed after him to Naderi 5515. I would love to know the significance of 5515, and maybe he can share that with us. He's frequently invited as a keynote motivational speaker at conferences and workshops, where he inspires the audience with wonders of space exploration. His university talks have taken him to some of the best academic institutions in the world, including my alma mater, Cal Berkeley. Firouz, come on up on stage.
Thank you very much. Normally, when I'm asked to give keynote speeches, the sponsor asks me, says, say something uplifting. Right? I must tell you, sitting here this morning listening to some of the really young, bright, accomplished founders, it was me who was uplifted. So I'm hoping I can return the favor in some small measure with this talk. Let's see if I can get the clicker. Okay, so tell me if the cycle I'm going to go through looks somewhat familiar with you somewhere along your adventure. You came up with a bright idea in the shower, sitting at a bar with your buddy. So next to write a spiffy pitch deck, you go to a venture capitalist, sell your idea. And since you are in a selling mode at that time, things look easy. I mean, profit is pouring in your lap, the food is sleeping in your mouth, and everything is good. And you get the money, right? You get started, and you find out that you didn't see all of the problems that were ahead. Some of them were visible, and some, so to speak, below the water, you had no idea. And that's the time when the pressures build. Typically, at least in my world, it is budget, it is schedule, and it is scope. If you get in trouble, one of these three it has to give. You just ask for the money. You can't, go give me more. Schedule, it's time to market, competition is doing something, you have to make it in a certain time. And the scope and the technology development is the other dimension. So now you're getting squeezed from all sides. And the question is, so what do you do now? This doesn't help. I've tried it, and more than often, it doesn't quite respond. So what happens? Your consumption of coffee goes up, sleepless nights starts, And really, at some time, it appears that you're expending a lot of energy, but the output isn't there. So somewhere in this process, either you or your teammates, likely your teammates, you literally either emotionally or physically hit a wall. And so if that happens to you, I want you to remember this talk, that you'll get through it, and that nothing is impossible. In fact, that is the title of my talk. And I want to tell you about something that we have undertaken. And if we could do that, I'm sure, and the word that I heard, and I think it might have been you, talked about perseverance, and that is the answer, that you will get through with perseverance. You get through seemingly impossible projects. And I'm going to tell you about 4 projects. 2 we have done, so it's not all promissory notes in the future. 2 we have actually accomplished. And 2 really, I must say, fairly complex missions are ahead of us and in the process of developing them. And I'm going to tell you about that. Hopefully, through that, you will see that you can get through almost anything, right? So the whole idea of what we're trying to do, we're trying to figure out if life exists anywhere else in the solar system except for us, on Earth. And the implication is, and of course, for those of you who have some knowledge of the extent of the universe, we're such a speck. This solar system of ours is such a speck that if life in this speck arose in 2 places, on Earth and somewhere else in the solar system, the chances that the universe is teeming with life exponentially goes up. So we are going to take a look at 2 places. One of them is the next planet next to us, Mars. And then towards the end, I'll talk about a moon of Jupiter called Europa, where we think if there is biology anywhere else right now in the solar system, chances are it may be in Europa for reasons that I will explain. So the missions that I will tell you about is mostly dedicated on these 2. So let me first talk about Mars and talk about the missions that we have actually accomplished, 2 of them. Mars really is difficult, right? The humanity, not only US, we have gone to Mars more than 50 times, and half of the time we have failed, right? Partially, it is difficult to get to. So the question is, how do we get to Mars? Right, so here we are going in orbit around the sun, Earth is, and Mars is going in orbit around the sun. And every 26 months, we get sort of close. If you call 34 million miles close, we get that close. And then most people have this thing, okay, so why don't we wait every 26 months when the 2 get close, and then we'll make a dash for it. As it turns out, that is not an energetically efficient way to go to Mars. So what do? We go a long way. Instead of going to where the planet is right now, we go 10 times longer, someplace in the future. We send the spacecraft, and hoping that the Mars and the spacecraft come together in one time, in one place, and the gravity of Mars gets a hold of the spacecraft and pulls it in. So the precision by which we have to navigate and plan where do we send the spacecraft is pretty hard. And I want to give you a sense of how difficult that is. And so the best way I can do that is to bring you back to Toronto. You remember? Yeah. You guys did it. Was a couple of months ago. Kawhi Leonard, the superstar here, is trying to, score the ball over a 7-footer in his face, and difficult, but you guys did it. But now let's make the problem a little bit more interesting. Unfortunately, and that's I'm sure a sour note for you guys, Kawhi Leonard is moving to Los Angeles next year, right? So he's going to Los Angeles next year, but just for fun. Let's keep the hoop in Toronto, right? And then ask him not to sink a 30-footer, but he needs to sink from Los Angeles a 2,500-mile basket from Los Angeles. And this is roughly the precision you need to make sure that the spacecraft and the planet come together at the same time. And I look around, and some of you don't seem to be all that impressed, so maybe make it a little bit harder. Let's move the hoop at 60,000 miles an hour, and then have him sink it. Because after all, Mars isn't just sitting there. Mars is moving. And so that is the precision you need to make sure that the spacecraft and the planet get there at the same time. Now, as difficult as that is, now after some 50 missions, we have figured it out. I think we can do that now with real precision. We can sink that, score that 2,500-mile basket. That we can do. But that's not and it takes, by the way, 8 months, somewhat depending on the opportunity, 6 to 8 months to go from Earth to Mars. That's the length of the trip. But it isn't that 8 months and the 350 million journey that kills you. It is the last 7 minutes. Most of the failures happens in the last 7 minutes. The spacecraft gets to the top of Mars, is traveling at 13,000 miles per hour or 6,000 kilometers per second. Okay, it's screaming towards Mars. And so in 7 minutes, it's gonna be on the ground one way or the other. Either you manage to soft land it, or it's gonna make $1 billion crater in the surface of Mars, and a lot of people will not be happy with you if that happens. So you need to come up with just a phenomenal brake system to make sure that you slow this thing down from 6 kilometers per second to a sort of a nice touchdown. So what we do is, the first step is, Mars, by the way, doesn't have much of an atmosphere. It has like only 1% of the Earth. But even the 1%, when you're going at 6,000 kilometers per second, you create a lot of friction, and that slows you down. But the negative part of it, it gets very hot. It gets about 3,500 degrees in front of the spacecraft, and if you're not protected, it's going to burn up. So we have to give it a heat shield, which is a sort of a material that it gets burned up. On this side is 3,500 feet. On the other side, where the spacecraft is, you can touch it. Okay, so that's the property of the heat shield. So you're going down, and it takes about 4 minutes, and you get down from that phenomenal speed to a supersonic speed, meaning twice the speed of sound. And at this junction, you deploy the largest supersonic parachute in the world. And where you do this thing, you're already at, when you fly, when I came from Los Angeles to Toronto, we fly, at 30,000 feet, 35,000 feet, maybe 10,000 meters. So we're there, we're going still really, really fast. And we deploy the parachute. Okay, so if you open up the parachute too soon, you're still going too fast, and the parachute is going to tear up. If you do it too late, there is not enough air left under you so that they can slow you down to touchdown. I'm not going to go through all the details of what happens during that 7 minutes. But there are something like about 60 things that need to happen precisely at the right time for this thing to succeed. And remember, the one-way light trip to Mars is about 10 minutes, right? So this whole process takes 7 minutes. There is nothing that you can command. It's not like the moon where you can joystick things, right? It is 10 minutes, so everything has to be pre-programmed and optimized for the landing. So anyway, if the parachute opens up at the right time, the next thing is that now you start some retro rockets to further slow you down. and you essentially come to zero velocity at a 15-story high building, right? That's where you are. You have taken most of the kinetic energy out, and now you are almost down to zero. And then at that time, we pop open an airbag with cocoons the entire spacecraft, and then we cut the cord, allow this thing to fall on the surface of Mars and bounce like a basketball until it comes to a rest. Then you deflate, and the spacecraft, the rover that he was asking about, emerges, right? So I'm going to show you a video, which is like about a minute and a half, which takes this process. Of course, a lot of it is animation because there is no CNN at Mars to observe this thing for posterity. But we have mixed in those of us in the control room that night where this thing happened, and mixed in with the animation. So let's play it and see how this 7 minutes of terror happens.
And lift off.
Has landed base pedal down, which means right side up.
No science analysis because it looks like nothing I've ever seen before in my life.
So, the process of developing this project took about 3 years. Normally it takes 5 for reasons I don't have time to go into. We had to do this thing more quickly, and at the peak, like about 1,000 people were working on it. I was in a control room where we landed. The excruciating part of this thing is that because of the 10-minute delay, now the spacecraft, something has happened to it, has landed or crashed into Mars, but you don't know for another 10 minutes, right? And so you wait until the young lady who was monitoring the radio. So if the signals start coming back, we know that the radio is healthy and therefore the spacecraft is healthy. And then she started screaming, I see it, and that's sort of the room erupted. And so I'm in a room, and CNN was in fact covering the room. And one of my buddies came and said, hey, Firouz, you're crying and you're on CNN. And I had absolutely no idea, that the tears were coming down. And it is that during the 3 years, you don't have the luxury of getting emotional. You sort of put all of your emotion into a jar and, tighten the lid and let it be there. It's no time to get emotional. You just have to be totally focused on the job that you're doing. And it is only after landing, it seems that like somebody took the lead out, and the emotions all come out. And just want to add something before I go to the next segment is that we were talking about diversity. We landed, of course, they don't give you a prize for just landing. You went there to do something. You went there to do exploration and, look at certain things. And the moment after we landed, we had a glitch, and a software glitch. And everybody was stumped. We didn't know what to do. And we had people of all ages on a project, from recent graduates to 40-year veterans. We had males and females, all sorts of ethnicity and all of that. And it was a very quiet, unassuming young woman engineer who figured out what was wrong. And not for her, even though we survived the 7 minutes of terror, the game would have been over. So fortunately, in my profession, the only thing that matters is your knowledge. And that's about it. And so, you learn, age goes away, gender goes away. Sometimes for those of us who have worked in that environment, outside is sort of like slap in the face, the way things go. I've found out now that I'm outside of that environment, and sometimes I consult for different companies, that not everyone exactly has that culture. But that is essential, that you become gender blind, you become color blind, you become age blind. The only thing that matters is that you're all committed to the same thing. So this was that mission, one of the ones that we had done. And the next one, 8 years later, we decided to do something bigger. Right? The one at the bottom, about 185 kilograms, is the one that we landed through the process that I showed you. Then we decided to do something which was about 5 times bigger, more massive, and it wouldn't fit in an airbag anymore. Right? So we had to come up with a new method of landing this thing. So some brilliant people came up with this landing that you will see in a second. It was so out of the box that the NASA boss at the time, the first time that we went to tell him, said, "You're crazy. This is not going to work," right? But it did. And so you will see the same thing now, landing the Curiosity in 2012, 7 years ago. And now, instead of airbag, we gave it a jetpack. It's a little James Bondish, but take a look at how we landed this much bigger rover.
We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky green. Sky green is started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars.
So consistent with the theme of my talk, yes, the hard things we do right away. Impossible takes a little bit longer, but we will get it done. And I particularly like the quote, I think it was heard, that says, betting against the consensus and then succeeding. That's basically what it takes to do, some of these missions. Okay, so those are the missions in our past. Now I want to tell you quickly about 2 missions in our future, which makes these two look like a child play, right? So the big thing is that every time we have gone to Mars is one way, right? We land robotically, but we have never brought anything back because it's difficult to launch from the surface of another planet without anybody being there, defying the gravity of Mars, and coming back. That we have not done. And why do we want to bring any samples back from Mars? Because if you're trying to look into whether Mars ever had any kind of a biology in its past history, you need really big, huge, sophisticated equipment and world-class scientists to be able to analyze the samples to tell you the history going back maybe billions of years ago. And what we can send one way to Mars, there are instruments which are confined in mass, in volume, and power because of the launch vehicle. Everything needs to shrink, so therefore they're not as sophisticated as something like this as you would have on Earth. So we need now to bring these samples back, and that's difficult. So what we're gonna do is next summer, almost exactly a year from now, we're gonna launch a rover to Mars that's gonna drill into rocks and regoliths and collect samples, and then put them in a test tube, right? And then drop them right there on Mars for future pickup. And we do this 30 times, and we get 30 samples, and it's scattered all over Mars, and that's all we can do with this single mission, right? Then a second mission that we're going to send, delivering it with a jetpack just like you saw here, we are going to send a launch vehicle that's gonna be able to lift off from Mars, which is this, and a little rover to go fetch all of these samples which has been thrown all around Mars and and bring it back. So here you see, this is the fetch rovers. Here are some of the samples that was left. I put a little red box out here. It picks these things up and sticks it into receptacles there, and then takes it back to where the rocket is, where the launch vehicle is. At the tip of it, there are these receptacles, and it takes all of those and puts them in here, and we close it up. At the time that we close it up, it becomes about the size of a soccer ball. So all of the samples are now inside of this thing, and we launch it. We launch it to space. But where does it go? Not to Earth. It puts that ball in an orbit around Mars for yet another mission to go and pick it up, right? So a third mission, it's gonna go and it's gonna look at this vast space around Mars with this little soccer ball going around, trying to find it, speaking of needle in a haystack, and then collect it and completely make sure that there is nothing from the surface of Mars that can contaminate Earth, and bring it back. Probably it's gonna take the next 10 years. The 3 missions together, Kamran Jan, even for you, it would be a bit too much to finance. It's probably going to be somewhere, the sum of the 3, about $4 or $5 billion. Okay, so, hey, look what you get for it. All right, so the last part of my talk is now let's go away from Mars and go to the moon of Jupiter called Europa. And so the next trip that I'm going to tell you about is to go there. And that also is going to take a sequence of 3 missions. So first of all, what is Europa? Europa is a moon of Jupiter, roughly about the size of our moon, same size. It was first discovered by Galileo 400 years ago. Because it was large enough. One thing about Europa is, yeah? Okay. So the whole thing is encrusted in ice. Some maybe about 30 kilometers thick ice. And then underneath that It is a huge ocean. To give you a sense, the deepest ocean on Earth is about a few kilometers. This is a 100-kilometer deep ocean and global. So in this thing, which is the size of our moon, there is 3 times as much water as all of the Earth's ocean put together. Okay, and so you say, why that far away from the sun we have liquid water? Because first of all, Jupiter is a beast. It's huge and has a huge gravity. And when Europa is going around it, it's not going around it in a perfect circle. So some places is a little bit closer to Jupiter and some places a little bit further away. And just like a rubber ball in your hands on how you squeeze it and it flexes. And that's what Jupiter does to Europa. Every 3.5 days as it goes around Jupiter, it keeps squeezing it, and that friction keeps the water liquid. And again, for reasons that we don't have time to go into, number one requirement for biology elsewhere is liquid water. If there is no liquid water, we have a hard time conceiving about genesis of life. So we need to get there. And we do that with, again, 3 missions. One we're working on right now at JPL. We're going to launch it in 2023. And it has a radar. And the job of it is to better understand the surface of Europa so that we know where we can safely land. And the other one is a radar to figure out the thickness of this ice, which is somewhere between maybe 5 to 30 kilometers, and we want to go to the right place so we can drill down. Then after that, we're going to send a lander to land on Europa and sample the size of it. And again, to show how science and politics can mix, we had a representative in Congress from Texas which loved Europa, and he was the head of appropriation committee, used to give us lots of money. Not anymore. He lost his election, right? So the fortune turned just like that. Now we're running around and trying to find funding again for Europa Lander, and I may see you, Kamran John, a little bit at the break. So finally, the last mission is that we are going to use we have to get to the ocean, and you have to melt through kilometers of ice. So we essentially use a warhead, a nuclear warhead, to melt our way through and drilled into the ocean. So the last movie clip that I'm going to show you, it is, some of you may know James Cameron, who was the director of Titanic. He also happens to be a passionate oceanographer. And so he made this thing his interpretation of how this mission might go. And surprisingly, it is fairly accurate, except for the last 2 seconds, which she sort of went Hollywood on us. And you will see what I mean in the last 2 seconds. But the rest of it is reasonably accurate. So let's go through, see how this mission would work. Yeah, that's where he lost me. We don't know of any octopus in Europa. So with that, let me just leave you with some final thoughts. And if we can bring back samples from Mars, or if we can go swimming in the ocean of Europa, what you undertake at some time in the cycle, you might hit a wall, physical or emotional, or some of your teammates might. But again, with perseverance, you're going to get through it. We can do this. You can follow your dreams, and you will accomplish it. Thank you for your time. Thank you. Thank you much. Thank you. Thank you. Thank you very much. Thank you very much.
We are short on time, and we're going to get our next panel started very quickly. But time for 2 questions from people who have not asked questions before, please. Let them get a chance, because that was fascinating discussion. You know how your parents always say, we want you to be a doctor, we want you to be an engineer, we want you to be a rocket scientist. Literally, we have one who made it. So questions from people who have not asked. Go ahead.
Okay, first of all, first of all, I cannot express how impressive this was, and I'm pretty sure everybody had the same feeling in the room. So 2 quick questions. One of them, I'm just really interested to know, what does it take you and your team to generate ideas as such? And secondly, I want to know, how do you do feasibility analysis for these type of projects? So, and maybe just as a last question, since I have the mic, where do you see yourself and NASA's project in 20 years? What's the plan next?
Surprisingly, the process is almost identical when you with the startup companies, right? So some engineer comes up with this idea, and the equivalent of your angel funds at JPL is some internal R&D funds. For $100,000 or so, we say, go ahead and develop it. And somewhere along that chain, we hit what you guys call an MVP. We do get something that they have now proved, yeah, that's feasible. Then we go for the next chunk of money, which again, in your lingo might have been Series A. We go to NASA headquarters, and we ask for the $5 million. And the $5 million comes, and we build something else which proves to them that this thing has a chance for succeed. And then we go for the really big chunk of money. So the process is very much the same. When I left NASA and I came out and started, consulting with the startup companies, it is that background, because I've been through that. It's a different ecosystem, but the process is the same, right? And so that's what happens. Next, I think, robotically, because NASA does different things, and I work in a place where we only do robotic exploration. I think the 2 missions that I told you about, the Mars sample return and Europa mission, which happens, and then NASA has announced that we're going back to the moon by 2024. That's more on the human side.
One more, very quickly, please.
Thank you. So impressive presentation and great videos. And so question that I have is, throughout your entire career, what has been the most difficult obstacle that you had to tackle, and how did you come out of it, went through it and come out of it?
I managed my career maybe with thought and maybe just by accident in 5-year chunks. Every time I got really comfortable doing something, I deliberately threw myself at a new challenge, and where I had to learn to get up to speed so I would be on par with everybody else, and it was that learning process that I liked. So I kept changing jobs probably 4 or 5 times. To give me a broad base. I never looked at it as obstacle per se. It just was another, for me, it was another learning opportunity. And I'm a curious person, so learning was just a reward. I also, honest to God, I thought that NASA is paying me to have fun, right? I never told my boss that, he might have gotten a different idea, but yeah, it was all fun. You don't last in a place for 36 years if you're not having fun.
Thank you.
Thank you.
Firouz Naderi.
Thank you.
Very much.